Okay, started.
Okay, hi everyone. So today we will continue back resiliency patterns discussions, which we had on 7.4. We discussed some of the patterns here, like bulkhead, circuit breaker, compensating transaction, and retry. Let me see. I think I need to mute some people here. So we discussed some of the patterns here. One of them was bulkhead, circuit breaker, and retry, and queue-based leveling, and we are to cover this leader election and health endpoint monitoring. So I'll briefly discuss what each of the pattern was for and internal what resiliency means and why it is important for any system that's being designed. So uh, as I was saying, like resiliency is the ability of system to gracefully handle and recover from failures. So I mean, like for any system, you want to design the failures tend to occur, and you need to be able to determine them and or isolate that specific system or like try to come back uh, to normal state as soon as possible, and that's all these patterns help with. Like if you haven't had a chance, I have already shared this link, and it's on Microsoft website, and it's has a good documentation and examples on C# as well. So the bulkhead pattern was like it's mainly to isolate your application into specific pools. This was discussed in the previous session. I can quickly show the diagram of this pattern just to get an idea. I won't go in detail because we have already covered. So just to give an idea to refresh your memory, it's where like imagine your system being built by services A, B, and C, and for some reason like the service A tends to be the bad one, and it's always I mean like either the load is very high and your resources are limited, and this service A tends to fail. And if you isolate the workload of service A from the rest of the services B and C, your system can still continue to serve the functionality which is being offered by service B and C, while the service A is still being bad or continue to come back up, or when it's failing. So this is just one example where you're isolating the workload of certain hot or critical functionalities from the rest, or just like try to isolate the functionality as much as possible so the failure can be isolated if it occurs. And this is for the multiple services. It can also happen that for a single service you can have multiple instances, and if the client is already if the bad client who may be making so many requests, if he is always connecting to one service instance, we can isolate we can still serve other clients traffic from other service instances. So this is the way you isolate the failures to specific small components as possible, so that your system can continue to be up. So this is about the summary of bulkhead. So, and the retry pattern, we know that like this is a standard pattern that we tend to use. So it could happen that most of the failures are like transient, like could be of the network or something. Like if you just try uh, another time, it might most likely to succeed. So this pattern is heavily used, and you know that like whenever the failure occurs, so if it is of like some network or timeout, so most likely if you try, it might uh, respond with success. And you can also add with retry with delay. So basically, first time you retry immediately, like within milliseconds, and you don't get, if you get a failure, then you increase delay exponentially. So that's retry with exponential delay. So just making sure, not exponential, like after some delay, which you might uh, increase exponentially depending on the error type. So this is about retry pattern summary. And the next pattern which is often used with retry is circuit breaker. So the circuit breaker is basically, it behaves like an electric circuit breaker. Like you typically have three kind of states in your application. So by default, it will be in closed state, your system. So whenever, and you have some threshold called like number of failures within certain time range. Uh, let's say, for an example, if it fails like 10 times within a minute, then you're going to trip the circuit breaker. Or like even within one, or like 10 failures within 1 second, then you're going to trip the circuit breaker. So you keep incrementing the failure counters in a normal operation. So if it hits the threshold within the certain time range, then you go to the open state. When your circuit breaker is in open state, that means that your system, if it's called by the applications or consumers, like the service, it's going to return failure immediately, and without even hitting the backend service. So you'll have some timer until when, like this is typically in open state. So once the timer expired, then you go to the half open state. So here you, when a request comes, you try to hit backend service and see whether it succeeds or not. If it succeeds, then you increment the success counter, and you will have some success threshold. Like if I hit 3 or 5 requests within a second, and if all of them succeed, then it means that the service is back up and working properly. Then you switch to the closed state. If not, like if it fails, you continue to return fail in half open state. So this is about circuit breaker. So this is often used with retry pattern. And the compensating transaction is basically where you have this is similar to like if you have a distributed transaction kind of a system where you need to update multiple systems to be in sync. So let me explain. So yeah, if you take an example of flight booking, just and if it spans of multiple flights and hotel reservations, so you know that like you have to execute all of them to be able to confirm the booking. So so each of these updates can be like on a different table or on a different system. So as you can see, all of this is a series of steps which needs to be completed to ensure that like you fully complete. So here, if something fails, you compensate the ticket booking. So like on every step, you normally would have reserved that suite, that flight seat to the specific passenger in the booking. So if something bad happens, then and you have completed until this point, you have to compensate all of the steps to be able to cancel the itinerary. So this is normally happens where you don't use distributed transactions, and you will have compensating logic. And this is typically happens in event driven architectures or event sourcing architectures. So where each system reacts to a certain event. And similarly for compensating transaction, you will have an event which triggers which tells the systems to revert that behavior or like revert that specific action. And we also looked at queue-based.
One quick question on compensating transactions, Naga.
Mhm.
Are there any existing libraries or anything like that which they talk about, or is it just like they mentioned only about the concept?
I think it's mainly the concept because the way you wire different systems is depends on your system architecture, right? Like, so for
Mhm,
example, all this ticket booking seats
mhm,
can be with the seat, maybe like seat booking or like maybe with a booking service, and this may be with a hotel service like hotel reservation service.
mhm,
So any cancellations on this seat bookings can be sent to the booking service. And if
mhm,
you have a queue where this booking service reads,
mhm,
and you basically place an event, a compensating event saying that roll back this seat reservation, that
mhm.
booking service, so it reads and acts accordingly.
Okay.
Similarly, you will have if a hotel booking service happens,
Mhm.
and
Yeah.
and if this is also an event-driven architecture, you'll place a similar event on
Yeah.
that.
Yeah. I
So
see more of an event-driven architecture pattern here. I was
yes,
just
correct.
wondering, like, because it's like the event goes there and make sure that happens, and event goes there. And
Hmm.
each microservice responds to it,
Hmm.
and then again, yeah.
Yeah, and if it
I
is
was
a
wondering maybe for
synchronous,
any other pattern there. Yeah.
yeah, if it is a synchronous instead of event-driven, then I think it's more of like orchestration, right? You
Mm.
know that like only if all of them complete will be able to commit that kind
Oh.
of, yeah. So another way is like using distributed transactions. You will have a coordinator which can establish the distributed transaction concept. We also discussed briefly previously, right? But
Oh.
that's the strongly consistent, but like it's not performance. It won't scale.
Mhm, mhm. Interesting. Okay. Thank you.
Mhm.
Is this similar to chain of responsibility pattern?
I don't know about that pattern, but like it looks, it appears. Can you tell me briefly about what chain of responsibility pattern works, how it works?
The chain of responsibility pattern, I mean, I felt it's kind of similar in the sense like um, it it behaves similar to event.
Driven.
Event
Okay.
event subscribe pattern itself. But the
Hmm.
thing is, like it moves in a sequential flow from one handler to another handler. So
Hmm.
which handler suits that, and it acts on it.
Okay. So I think maybe it's slightly, maybe it su- kind of supports, or I don't know what is the term to say that, but essentially this is, it need not be a chain kind of a thing, but the idea of compensating is that like for every successful transaction or like successful data updates actions, you'll have some compensating if something bad happens in this compensating. Basically this compensating happens only when you have multiple systems to be updated for a certain transaction, right? So and if one of them goes bad, you need to compensate all of others. So
Yeah.
if you have charged the customer, the compensating could be a refund or like full refund or something like that.
Yeah, I
Uh,
would like to add to this. This is Prashant here.
mhm,
So, chain of responsibility, for example, you can consider exception handling scenarios, right?
mhm,
So, in one case, we are handling exception one. If it
mhm.
throws exception two, it is not handled, and it goes up in the hierarchy,
Okay.
right?
Yeah,
So
yeah, yeah, correct,
that is
correct.
a completely different topic.
Mhm.
Maybe
Yes.
some association,
Mhm.
but in case of the compensating transactions, it is like a rollback mechanism. For this step,
Yeah.
if it fails, what is the rollback solution you have?
Yes,
So
correct.
those two are different concepts actually.
Mhm.
I
Yeah,
I don't
Thanks
know
for
if it's always rollback, right? It can be any action.
Yeah, any action. Yeah,
Eh,
that. I
For
think
every action, there is like either a success or some other action to complete that action.
Yeah, compensate. Basically, yeah, it could
It
be a
says
rollback.
compensate. Yeah,
Yeah.
it says compensating, right? So
Hmm.
if it is a success, if something happens wrong, right? That's what I felt. Resiliency, right? If something fails, what do you do to
Yes,
uh,
correct.
to come
Hmm.
back to the original state?
Yes,
Oh,
that's, yeah,
only
yeah,
handling
that's the right
failures.
term
That's it.
for compensating. Yes,
So,
correct.
so in my experience, like I was asked an interview question, and I think it's the same thing. So, here a transaction. So we know what a transaction is. Transaction is that everything should happen completely or everything should not happen. So here a transaction is defined by multiple API calls. Like in this case, a transaction is defined by 5 API calls, right?
Mm-hmm.
Now, if I'm writing my service, I have to write my service in such a way so I can only make those API calls. I have to write my service in such a way that either all those 5 should succeed and then I should return success to the customer. Or if any one of the fails, then whatever I have done in the past to make that transaction, I need to roll back so that everything is reverted back, right? So this is what we are doing in this, if I'm understanding it right.
Okay. So all of
As
them
I
have to be successful or all of them have to be cancelled?
Oh, yeah, so a transaction is defined by everything succeeds or everything fails. So here,
Yeah, just to clarify that understanding, yeah, I think the intention is right, but the way it behaves is not exactly like distributed transaction. So I think the concept you are trying to, I mean, like the typical transaction is like even in RDBMS or anywhere, all of them happen or nothing happens, right? Like when you have multiple table updates.
right,
But um, the way distributed transaction and compensating transaction differs is, in a distributed transaction setting, you wait for all of the systems to commit to complete the transaction, or you before you commit itself, like you will get a handshake from all of the systems that they are willing to commit or not. So, but like the difference here is, this is more comes in kind of event sourcing architectures where it is acting on a certain event and it is not working in a synchronous setting like distributed transaction. It is similar concept, but the action was previously completed for some of the steps like book seat one on flight one and flight two. And if some when booking the seat on flight three, it happened that like it was not available. In this, the behavior could be, we can offer some other flights which are available in the same route to the customer, and probably they can choose, or like some other route, still holding these reservations. That could be another compensating logic instead of just canceling on this the previous two. So yeah, this compensating does not literally mean rollback. There could be some other behaviors like offering another flight, or like maybe offering another hotel. Say that like this booking flight booking was successful, but the hotel that he is booking, customer is booking, may not be available, or like or high price. So he just wants to book another hotel and retain the same booking that he had. That could be possible, right, in the compensating logic, but
right.
not in distributed transaction setting.
So Naga, are we saying that this all these actions are happening serially, like one after the another?
Yeah, I mean, like, don't just look like this, but like it happens that like, yeah, this is more of like, treat it like in event sourcing, you basically just put one message to book it. So like, imagine like having one system and which says like, this is successfully booked, and whoever system is basically waiting to confirm this itinerary will actually wait for all such events, for all of this. So imagine like if these three were successful and hotel booking was not, then the compensating logic could be offer another hotel, or like if offer the option back to the customer. So you have some extra behavior here, asking the customer to involve in this decision, either to cancel the full itinerary, in which case you really roll back all the previous ones, or like choose another hotel where you only make alternate hotel bookings. So this is kind of a behavior which normally during design you think about those, like whether your business is okay to do compensating, or you want to do like a strict before committing itself, you want to ensure all of them can be committed, or if not, like abort or cancel that. So in such a way, like it's kind of a synchronous, like distributed transaction.
Yeah, I can give a real life example of this piece in Microsoft.
Mm-hmm.
Uh, think like a customer is buying something from Microsoft, let's say a VM in Azure.
Mm-hmm.
They place a request, submit. It takes a little bit of time to do some risk check, some events. Some are sync in nature when everything looks good. Okay, it gives a success to the customer. And behind the scene, the next event try to charge to a credit card or so. If that fails, then you refund. If that succeed, then you try to provision the VM. If VM provisioning fails, there is not enough resource in a particular data center or so, it can fail. And then in the compensation, the events that has been placed, which is a charged event and all that, or those need to be refunded. And per my understanding of this pattern, it is for an automated way. Now, when the manual thing comes, it's probably, that's my understanding. I might be wrong here though. The example that was given earlier, where somebody from a customer service trying to reach a customer that this flight is gone or this hotel is gone and try to do something else. That's not probably a pattern. That's a manual way to fix the
Yeah.
transaction that is stuck in a state.
Yeah, that's correct, Hitesh. Like, yeah, I really meant it to be like the system, like the web screen offering the alternate option, not the customer, a person involved in this. It's basically, yeah, everything is in an automated way. Basically, we have a system doing all these actions because, yeah.
And I think if system is not able to resolve this, then the compensating logic could be this, that send a email that
Yeah,
something went
correct.
wrong and reach out to the customer service to resolve your issue.
Yeah, correct. So you basically, this is decisions done by like normally if you are a senior engineer, you normally work with product people, like how they want this behavior to be. So if, whether to go in automated route, like, or do this kind of like manual actions if it's okay.
Yep.
I see Meet is raising his hand. I don't know, like, do you want to ask question or speak up or like provide your opinion? Hello. I don't know. Yeah. Okay. Let's continue. Okay. That was a fruitful discussion. So let's go back to the other patterns. So one of the other thing which we discussed also, so I'll go over briefly, is a queue-based load leveling pattern. So the idea of this is like you have, let me see if this is, okay. So you have a certain service which is handling the messages at a certain speed. So imagine like if you have certain calling applications or tasks, if they're directly talking to the service, and it may happen that at certain times, like when it's a peak time, if all of these consumer tasks or like applications directly talk to the service, and if the load is higher than it can actually serve at that point, then I mean, like, it's likely that this is going to fail, or like errors for certain few I mean, like some percentage of messages or like requests. So typically, but like if you know that the load is normal or like less, that this service can normally handle at most of the other times, except few times where it's going load more than this can handle. So you typically add a message queue to soften or like smoothen the load. and you have all the calling clients to place a message into the queue that is consumed by the service, and this service can always continually process the message in a standard pace. So yeah, if you see this diagram, it kind of highlights what I'm trying to say. So there is another better diagram, like imagine all of this talking to a single database and it times out, and you basically add a queue where all of this try to put messages here. And this is an example of Microsoft Lambda function. I think it's a function app which actually processes a message and updates the data store. So here it can actually process in its own pace. So any questions
I
on
think
this?
the challenge here is
Question.
the
Mhm.
I think the challenge here is response back, right?
Yeah,
Some
correct.
is how the application knows about it. Yeah.
Yeah, so basically, but this pattern can't be used like if you want immediate response, um, because like if you place into the message queue, it's async, right? Like you can have another response queue where you can wait for the message. If it's okay, you can do that. But if you want like a synchronous behavior and instant response as soon as you hit the service, then maybe other ways to scale the service. So the moment you add another service to increase the load, you are increasing the resources and the cost also, right?
Right.
So adding,
Yeah.
yeah.
We
So,
can also use the message queue like a database instead of the message queue as well, right? To for the same behavior instead of the message.
are you saying use a queue as a database here?
Yeah, we can add like a database over there, so all the tasks that are coming in that can be picked up by the service from that database. And
No, that doesn't work quite well as the message queue because um, the database still have again restrictions on the number of connections clients can take, similar limits like a service. So it again depends on the database limits, but the queues are good enough to accept as many messages as possible because it doesn't ensure you any ordering as such if you use a normal queues. So they're typically scalable and yeah, and it can smoothen this kind of a patterns.
Yeah, exactly, right. These are queues are like easily scalable, and then when you consider database, right? You
But
Yeah,
I
can
think,
scale
cost
up
is
fast
quite
and
less. Cost
the
is
cost
quite
is
less
also quite.
compared to databases.
the Raza was mentioning like you can use the database also as a queue, right? Like the Redis, it's a database, but you can use it as a queue.
Oh yeah, you mean like yeah, when we say queue, actually it is internally a database, but it is not like a typical other databases that we are talking about. So queue, since it needs to persist the messages I mean like at least for the period the service is consuming like permanently. Like when we are placing messages into the queue, it means that the messages are durable. So unlike service like when you are making a network call, like a REST call, it can be lost somewhere, but not the case with you, right? Like because it gives you durability. So it means that like it's kind of internally implicit database. Um, if you think in that perspective,
Yeah,
it
there
Right.
is
actually.
some advantage of a queue versus database. Like different team uses both the options are in use today.
Mhm.
Uh, there is also an advantage of using database. Some team use database, like my team also uses database. The way
Mhm.
they do is a SQL table, which is append only. You keep putting the data there so
Mhm.
that it can be consumed by the consumer. The restriction with the message bus or message queue in Azure, it has certain days limit that when you put it, there are listener to
Yeah,
those
yeah,
data.
correct, correct. Yeah, yeah, correct.
But when you deal with the database,
Mhm.
you it's a persisted there. It will always remain there. If you would like to reprocess some data that was sent 5 days back or 5 months back or something, or might be building a new service that has to read all the data, there was an issue that you might have to read pretty old data. So both the patterns are in use, or both the type of queues, whether you treat it like a database or you treat like a message queue, they are in use. And it all depends on your consumption pattern. That do you need to go back? Do you ever need to go back, far enough to read the older data? Probably in that scenario, the message queue or Azure, it has certain limit. It is very costly affair if you use a queue to retain data for more than 3 months, or the more you go in
Yeah,
Azure.
the bad. Yeah, I agree with you because the queues are meant to be short term because it is just to, I mean, like in this scenario, if you just want to smoothen the load, like for peak times only, so that's where you are using, right? So if you think about a scenario, this service is, if something bad happens, like you need to make sure, if suppose if the service fails, you need to have a mechanism to monitor this queue. So like if this queue is continuously having messages more than intended, or like which this service is not processing on time, then you basically have some mechanisms to spin up a backup service, or like to see what's going on with the service. So you don't have messages lying in the message queue for a long time. Even Amazon, I think, has limits of default of 14 days, or like I don't know, even 4 days for some types of queues. So it depends on your setting, but like mostly the default setting is not more than a couple of weeks. So which is huge actually, because you tend to process these messages as quick as possible as soon as they're placed. If this service is really up to speed, processing in its own pace.
So Naga, one question: is load leveling is same as load balancing? The queue based in the title, the queue based load leveling.
Yeah, kind of, but like not exactly. So here, like we just talked about one service, right? Like we can also add another services. Like if we know the service takes each time it picks up a message, if it's not processing, if it takes some time to process this message, then it's typically that one service might not be able to process if the messages are coming in a faster way than this consumes. In that case, you basically need another services to consume. So as soon as this service picks up the message here, this will be invisible for other services. So the other service will actually pick next message and process. So it depends on how fast these messages are coming and how fast this service is processing. So accordingly, you add another service instances to distribute the load.
Okay.
So load, one thing to just quickly add, load balancer. So in this case, right, when your services is getting reading message from the message queue, nobody's pushing, basically maybe service is polling, right? In that case, load balancer will not come into picture. Maybe multiple service, we can increase the instance so that the increased message queue length we can decrease. Load balancer mostly come into the picture when there is an incoming call in case of API. For example, there are many users calling and you have a end instance of service, then you want to distribute that load equally among all. So that's where the load balancer come into picture.
Question: suppose your service is auto scalable, and depending on the load, so you will call it the right hand side, which is a service which is auto scalable, maybe using Databricks or so, depending on the message queue size. That we will call as a load balancer, right?
What is load balancer in that case if service is auto scalable?
Yeah, there is no load balancer at all there. It's because the service itself scales, right? Like say, take this example. If you have a Lambda function kind of like, I think Azure calls it function app, so which can pick the messages and process in its own pace. So this Lambdas will be invoked as soon as these functions will be invoked as soon as there is a message placed into this queue. So this can grow in like quite a number. So because that's kind of auto scaling, right? Like that's where like now mostly the serverless patterns came in. So if you have that kind of a pattern, you don't have any load balancer. As soon as some message is placed into the queue, you have some trigger to invoke this function app, which can process this message.
Oh,
So
yeah.
this invocations grow in the number similar to the messages placed in this queue.
Yeah, when I said load balancer, I did not mean to have a separate component which is balancing the load, especially.
Yeah.
I mean, if his service is able to auto scale itself, then it is handling the load itself. It's balancing the load itself, actually.
Yes, correct. Yeah. But if take an example, this can scale depending on the messages, but your database will definitely have certain limit. So it's again, you need to ensure that this component is also scaled along with this. So to be able to truly scale. If all of these apps are talking to the same database, then it will have certain limit. So you'll need to partition or replicate and do some scaling here also on database perspective. Okay. There are no questions. Maybe we can switch to the other pattern. So let's talk about the leader election. So this is the pattern which we didn't cover in the last session. It's basically the leader election pattern is basically when you have certain set of actions which can be performed by multiple instances, and if you want to aggregate the result from all the instances, you need to have some kind of a leader which can coordinate those kind of tasks, right? So an example of this is you typically have, like if you have wherever you are scaling, you typically have a zookeeper which is electing the leader and which is actually coordinating all that stuff. Let me see if there is a diagram to explain this. No, there is no diagram, but like this pattern mainly is where you normally have multiple instances of the certain service, and if all of them are performing similar thing and one of them needs to act as a leader, and the approach of electing a leader could be you can choose based on the instance ID, or like you can have a race condition having one mutex like from OS level, and have all the instances to see who can or all the nodes to see who can acquire that. Whoever acquires that distributed or shared mutex will be able to become the leader. So that can be one approach, and there are also some other algorithms to elect leader. And the leader is normally like these are the things that we normally need to consider when choosing a leader. So we need to make sure that leader should be resilient to the failures, like whether it's temporary or permanent. So there should be a mechanism to identify whether the leader is still up and running, or like or dead, and we need to spin up another leader. There should be another leader election. So so typically you'll have some kind of heartbeat monitoring by other systems on a leader. Anything. And when to use this pattern is basically yeah, as I said, like whenever we need to coordinate the work of multiple nodes or instances, only in those cases like we will need to have a leader. So if you don't see there is a need for leader, like some person to coordinate all those tasks, then you don't need to use this kind of leader election. I think they have given an example of distributed mutex from C# standpoint. I mean, like for C#, you can actually try to read this offline. I think I went fast. Is there any questions on this pattern before we go to the others, or like anybody wants to share?
Can we go into a little more detail about electing a leader?
Yeah, electing a leader is again like complicated. Like in a simple terms, as I told, like it could be happen that like you can pick whoever is having the lowest ID. Like if you are using integer IDs, you can pick randomly the one with lowest ID, or you know how the racing condition works. Like if there are multiple threads racing to acquire some resource, so the resource could be a shared variable or like a mutex in operating systems concept. So this mutex, like there can be only one person who can one thread which can acquire, right? Basically, if you are having one shared, to be able to see like whoever acquires this mutex, they can become the leader. So this step involves like operating system operating concepts. Tell me, someone, Naga, are you having some?
Yeah, yeah. I think that's in general. Like I was thinking in terms of the Kafka clusters also have the similar concept, right? They have leader and like
Yes,
replicas.
correct.
Does it
Yes,
also, is it the, okay? It's similar pattern, right?
yes, correct.
Okay. So in
So
case of Kafka,
their
right?
zookeeper helps in electing the leader. For
Yeah, zookeeper
normally, they
helps in
typically be used with zookeeper.
and like
If,
there's no affinity on like who can be leader, right? There's in that
yeah,
anybody
yeah.
can be leader. It's just
Anybody can
that,
be the leader there. Yes, correct.
yeah. There it is like usually the transactions happen directly with the leader, and leader is responsible to do the replication. If
Yes, correct.
leader goes down,
Mm-hmm.
any of the replication can be taken as the leader, and
Yes, correct.
yeah, that's one example. But there was no affinity on who will be the leader. I think here there is an affinity on who can be the leader, right? In the example operating system.
Yeah, so this leader election mostly may be used for like where you have leader-based systems, right? Like the single leader applications wherever you have. Even most of the databases, if you see, including DynamoDB, or like even they use single leader or MongoDB. They mostly have one leader which accepts all the writes, and they have multiple like replicas which serve all the read traffic and other things. So,
Oh, okay. Thank you.
and if something happens to the leader, then one of the replicated nodes should become the leader. So, and choosing the leader again involves like a lot of items to consider, right? So we need to see which of the replica is most latest up to date, considering the leader's data and previous data. Or it could happen that, I mean, like if it happens that whoever acquires this mutex, they can become the leader. In that case, it will be a race condition. And yeah, and there are many other algorithms in choosing a leader. So typically, when choosing the leader involves a consensus decision, like all of the nodes needs to agree. So whenever all the nodes needs to agree on one node becoming a leader, it's a tough job. That's why most systems typically use the zookeeper, which already implemented this consensus or those protocols, and they internally handle all this. And there are many other algorithms like consensus algorithms like Raft and other stuff, which is again where we can go in depth. So it require its own. If you are studying designing data intensive, they give an idea on this consensus in later chapters. I think maybe 8 or 9. So he has clearly explained what is total order broadcast consensus, and what's all the prerequisites, and what's the importance of ordering to ensure that.
Yeah, yeah. I think one more interesting point is like a leader node is a leader node only for certain set of operations, right? In case of
Yes,
Kafka
correct.
cluster is like it is a it's a follower for certain other operations, and it's leader only for certain set of operations. That way it is uh, I don't know what is that scaling maintained or replication maintained by using.
It depends on the kind of, if you see the typical database implementations, leader means since they handle all the rights, they'll have the latest data, right? So they have strictly one leader most of the systems, and there are other systems where kind of leaderless, but they internally choose a leader for every request. One of them can be the leader for other requests, other one can kind of coordinating in that case, for
Yeah.
mostly in leaderless systems. So Kafka has, I think, both approaches, leaderless as well as the leader based.
Yeah,
So
yeah.
it depends on what implementations we choose, or I think it internally uses both. That's what I read.
Yep.
So to add to what you guys put a point, yes, database can have this pattern used, and your service also, your code can have that pattern. For example,
yes, correct. Yeah.
Within the system, you want certain tasks to be handled only by one person, right? For the before example where we are talking about queue, we were talking about when the load increase, I want to increase instance of my service. For example, there is external things that does that, or in your service only you have a code to do that. Basically, if the queue size goes certain threshold, I want to increase one more instance. So, but you don't want all your instance to do that task, right? So you implement one of this leader algorithm so that one of the instance can acquire and keep checking, keep tab on queue. And if that instance kills, then somebody else can acquire that global lock and keep doing that. So at least one of the system is keep doing that singleton task at your distributed system level.
Okay. Yes, I agree. It's may not be just with the nodes, but it can also be on the tasks which are all doing. Yeah, wherever we need that coordination, it's good to have one leader doing.
Yeah. So one question, Naga. So once a leader is elected, they remain the leader till the time there is a failure with them, or is there something like a round robin, or will they relinquish or in some scenario?
It depends on, mostly I think it's till the failure. That's how mostly single leader systems behave. But it depends, if your scenario needs to shuffle just to ensure all of them get an equal chance to become a leader. If all of them can be the leader, then in that case you can have round robin. In some instances, it may happen that only one of them are more eligible to become a leader. In those cases, you don't have many nodes or many participating instances or tasks to become a leader and process.
Yeah, I don't see a scenario where the leadership has to be shared across, right?
Yes.
It's not necessary that the leadership has to go to all these things.
Yeah, correct.
It's more of so I'm again coming back to the example of Kafka cluster, right? So it's you say for certain set of data, this is the leader, and that's handling all the reads and writes, and its responsibility is to replicate to other two places, just in case this node goes down, we have some other place to go to. I don't know, it's called availability, right? High availability, to maintain the high availability.
Yes, correct.
Right. Yeah. So, and if this goes down, then somebody takes it, because this node has go down, and we want to maintain high availability, and then the other one takes the leadership, and it also makes sure there is another replica available, because we always have to make sure there is another replica available. Yeah.
Yes.
But I
Yeah,
think
that's right.
in that scenario, it's not like whoever serves the data, it doesn't matter, right? I mean, leader is just
Yeah.
responsibility. It's like it need not be passed around. I don't see a need for passing around, but there could be a scenario.
Yeah, it's as simple as one. There is a task that only one need to perform, and that's where we, when distributed system, when they are autonomous, this is in place so that only one guy is doing that task. Only one node or one service is doing that task.
Oh,
It
exactly.
does. Yeah, it doesn't entitle anything. So that it's not that we have to be fair so that everybody is leader.
Yeah. Yeah. The naming probably is like.
Yeah, exactly.
And like, should we also consider, like, in case I'm talking about the worst case scenario in which two distinct processes are got elected as a leader due to something, like, or I mean, should we consider these cases and also code our app with that consideration in mind, or we should just rely on this leader election softwares?
Yeah, it's basically this algorithms normally tend to take care, but it can happen that the two instances, if you are not carefully choosing your algorithm, it may happen that both of them can become the leader, and it can go to the like split brain example. If this is mainly to if you coordinate certain data, I mean, like, or like if you take an example of database, if both of them are accepting right, then you tend to lose certain rights because it's not properly replicated across.
So one thing, so what I hear question is leader election software, right? So see, this is a pattern. What I understood is that you have either a software implement any of one of the pattern internally, or if you are implementing in your service, you have to code it, right? And the way we code it is, if you, in this article itself, in the down, they have said, written that what you have to consider when you are using that pattern. And one of these things is that, only one can be elected as a leader. So, for example, at the OS level, within the process, if you are acquiring a mutex, there is no way, OS guarantee that there is no way that two person can acquire that mutex, right? So that is a leader. I can say that leader election pattern within the process. Now, at the distributed level, whatever way you want to achieve that, right? There are a lot of other. I just know only one way. In Azure, you can have a global storage account, and somebody can log the storage account. Now the storage account, blob storage, you can log. Now, blob storage, whoever is providing, they can say that only one person or one, only I will allow only one, someone, only one, call to acquire that log. So there is no way that that there are two leader can happen if you have implement this pattern using, let's say, blob storage.
Yeah, I mean, like, if that happens, then there is a bug in the pattern.
Yeah, exactly. So then pattern is not correct.
Yeah, it's not a feature that everyone will handle. The software has a bug that needs to be fixed.
Yeah, that's where, like, if you have that consensus among all the nodes of like agreement properly, then that scenario most likely won't happen. So that's where, like, you need to be able to choose right algorithms there, or like right systems which have implemented those algorithms, which ensure that they don't allow such scenarios.
Yeah. The consensus before this picks the leadership, it has to make sure there's nobody is a leader.
Yeah, disagreeing or something. Yeah.
So one more question, Naga. Yeah, so someone was saying the load balancing on the leader election round robin and this all right. I heard, I mean, I was aware of this one as well, but not sure where it is used or something. There's a prefer, I mean, if some, there's a prefer, I mean, in Kafka, there's a preferred leader election as well. Even if someone is already existing as a leader, you want to replace with another leader.
You want to replace with another.
No, I mean, like, is there? I mean, like, there could be some reason why they're planning to replace, right?
I don't know that. That's why I was asking. Since it was that topic.
Yeah, I think let's. I think this is a good topic to discuss a lot because I think it involves. I'm thinking to take this consensus topic sometime and probably choose one of the algorithms like Raft or the famous Paxos, which Paxos algorithm is basically most used in leader election. So I mean, like, and it's quite complicated to understand. So let's take that as a separate one system design topic, and I'll probably and we can cover that at some point. Let me add Paxos somewhere. Okay. So yeah, I think one other thing is the health endpoint. I mean, like, this is just to have a health check on your systems, like for any resources like databases, your services, and if some calling applications or clients wants to monitor or like ensure you the health status is green before invoking, like the service is up or database is up, and yeah, just to ensure that like all systems are up, you need to offer basically a health check endpoints for all of your systems, just to make sure that to indicate your system is up and running and can serve the incoming traffic. So this is an important from monitoring and availability perspective. So most systems offer this, and some of the careful considerations that you need to do is like whether you want to keep 200 OK as available, like if you are offering an API or like any service which responds to 200, you consider it without an error or not. And the SSL certificates, the DNS lookups, you want to make sure that like all of this return the status correctly. I see like mostly the SSL certificates is something which you normally ignore, like, or don't catch often. Anything else? Yeah, I mean, like, this is a straightforward pattern. We typically expose this endpoints like on port 80 or 443. Like, I think mostly they do 443 because otherwise some systems anybody can call unless it's publicly available. You normally expose this Healthcheck endpoint on secure port. So I think, and any other important things is basically, let me see if there is another thing to consider. Yeah, when to use this pattern, just to verify the availability, to see the correct operation is available, and if there is a failure to isolate it or like not invoke those services if they are not available.
So is it expected to use by the consumers, or is it expected only for the maintenance of the service?
It can be for both, right? Like if typically it's mainly for the system monitoring, like the monitoring systems, whichever we have, they tend to always continuously poll this health check endpoints to make sure that the systems are up. If this health check endpoints return, say, some system has down and that can't be down and it's a critical system, you can have an alert system or like a 7 incident raised that like somebody can quickly resolve based on the SLA. They need to take the action accordingly. So, or if it's a low important system, it's like you may just have a 7 or low priority or like low priority incident, which can be taken even few days to bring it back up.
But I mean, see, I think instead of having this health check endpoints, right? Why not have a pattern where like you check the end-to-end functionality? Because just because the health check endpoint is available, it's not necessary that application is working fine, right?
At least you know that it can return errors, like when you that's what like so when you choose like how do you decide the application is up and working normally? So that's something that you need to design like around like when do you say this health check as part of health check API, like when you return 200, does it mean like your service is up and running and it can process any request? Or it just simply means that your system or like services server is started and then that's it. Yeah, I mean like that's kind of an understanding where you need to
I think this
say
it's like abstraction. You up to us what we want to do behind the scenes.
Yeah, correct.
So if Naga, you said if you monitor your service end to end, and if then your service is failing, then it's too late because now your end to end scenario is broken. So what you generally do is, whatever are the smaller components of your service, you monitor them, and in your overall service, you will have a retry logic and stuff like that, so that overall service is working fine. But you are also monitoring individual components. And if you see the health of individual component is not good, then it might be possible that your overall service might start failing. So that's why you have those monitors at individual components level, so that it's not too late.
I agree on that. I mean, individual components, we have to do it. But when we check this individual components, should we, I've seen like having that health check endpoint, specific health check endpoints, it doesn't really do the functionality of the service, but it's just like if the endpoint is up and up, right? Typically, I've seen the health check endpoints like that. It's just like you have a specific controller, like health check controller, which just says like, okay, this service is up. But
no, Naga.
not really.
You can actually add much information to that health checkpoint as well. I mean, the CPU says. I mean, I have seen services with that health point returning other information just other than just okay or something like that. I mean, you can send CPU memory, how many, what is the load on that. You can send many things actually.
Yeah.
Also is the functionality, right?
I feel like there are other things which does the same thing. So we need to think like, are we overkilling this health check? Because I've seen like things like EC2 health and other things, or like on any cloud infrastructure, they also monitor the CPU and your response rates, like how many 200s, 500s, 400s are coming. So it could be like separation of concerns to me. Like what we want to do here could be an application functionality, and there would be other points where we can even check the overall system health.
Yeah, I think this is a node level health. You basically, suppose you have a 20 instance. That is a system that basically keep pinging, right? All 20 and make sure that all are okay. Now, inside, most of the time what you do is that, okay, do I have all the information that require this node to run? For example, if you need access to certain secrets, do I have that access to that secret? If not, then I'm going to return, that 200 has failed. Or if everything is okay, then I'm just going to return. I'm not going to do some end-to-end test or not even the scenario test in that case. It's just that do I have enough to run my service? This is very helpful in normal when suppose load is CPU is overloaded, then the 200 takes really long time to return, so that if there's a load balancer, they can take a decision saying that this node is not returning 200 to me in time, or not returning at all, so I'm not going to send any request to that node if it is API node, right? In other case, when suppose you are doing deployment, right, you basically do phase by phase. You have a 20 instance, you do, let's say, 20% you basically deploy new bits in 20% of the instance. So for instance, you deploy. After deployment also, basically we do HTTP 200 and make sure that the deployment infrastructure makes sure that that node is working or not. And inside the you can handle it, saying that what you want to do. Most of the time I have seen that we see that, oh, all the secret or all the things that I need is available or not. You basically try to construct your object end to end, just construct, nothing else, so that, oh, that you have a connectivity up to database level if that node is doing that work. There's no runtime error.
Okay.
So this kind of thing we typically put in that.
So it can be like at any levels that we want. Can we say?
Yeah, but we definitely avoid, as pointed by others, right? Any end-to-end testing. It is just that we want to say that this node is healthy or not. Is it ready to take request or not?
Okay.
After the deployment, the node is healthy with all the bits. That's the thing we want to test.
Yep.
So
makes sense.
This is really helpful when we do something like a rolling deployment, where I want to upgrade with new code, but at the same time, if something goes wrong, just roll back to the previous one.
Yeah.
Okay. Yep. Makes sense.
Why do we need the agent? Can we just query directly why we need to install the agent on the node?
You mean like on
if you scroll up,
agents?
If you scroll up in the picture.
Okay.
Push and pull based, I think so.
Do we install the agent on that node, or the agent is like a separate
this
node?
agent is basically the one which is monitoring, actually. So you need to have a system like you can have all the systems in your application, and there needs to be a monitoring agent which can actually continuously pull all of this and ensure that it's returning what you're supposed to return.
Is it one agent per machine or per application, or one agent for all the applications?
I think for all, right? Like you usually have one monitoring for all of your application, right? Like one system, maybe like if you're using, I don't know, Neural Lake, Datadog, or whatever that you have, whatever the system that you normally have, which is monitoring all the systems, you basically use the same system to ensure that the health is good for all of your applications system.
It's more like you have a test which is running against the application that is shown here is the one that you own it, and you have some test which is always checking that application, and there could be multiple clients using it, or like other services using it. It's the agent is like your own application or your test case or your tool, whatever tool that you are using to monitor this application.
So I think like if the agent lives inside or outside, it depends. If you are the owner of the application, probably you can have agent inside the application. But if you are using some external API and you are not the owner, then you will have some external agent that will make a call to that application and see whether it is up and running or not.
So aren't we going so aren't we going opposite of the high availability and all those things and going into a single point of failure type of system, because now agent is a one service, right?
No, agent is a test case. So no one is agent.
So I think I have a different thought on that. I believe that, see, if you are using load balancer, right? Load balancer also call each node HTTP 200, right? So in that case, load balancer can be agent.
Yeah, makes sense. Yes.
See, agent, yeah. So and when you are deploying, right, the application that orchestrate the deployment, the rolling deployment, that is the agent.
I have seen some cases that the agent is installed. You know, the application or the machine have to install the agent to be able to monitor. And
so that is different thing, right? So probably that is okay. For example, how we can get the CPU data out of each node. So either you do install something or something that operating system already give, and then you basically just monitor that. There need to be something on the system that basically monitor, collect that data and send it somewhere. CPU memory uses. A lot of time I have seen the distributed logs, right? There is an agent on the local system. When application write the log, it's not that each log goes to the server and go. Basically, it collects locally, and then at the regular interval, let's say every 5 minutes, every few minutes, it upload to the server. So when you say that we have to have an agent, right? It's maybe it is for that specific purpose, right?
Yeah. Okay. But if the application already provided, then we don't need it, right? Okay.
Yeah.
So, and are the services are supposed to check with this Healthcheck point before making the queries to the actual services? Is that right?
It depends on how you have your application designed, right? Like if you have another third-party system which is already monitoring and ensuring the availability, I think that is just to make sure that you have availability. Your services can assume and try to invoke that they're available, and yeah, and whenever something bad happens, this agent can alert and make sure that that system can bring back. So if for example, if the consumer calls a system which is down, they get at least like 500 or something, and they know that they can't invoke until it's back up. I don't know.
I want to understand that question probably. Okay. What is the question?
So I was saying, like, what is the use of this agent? So I know from the diagram, it looks like it is gathering all the required information and checking, okay, overall, all these components of our system are up, like CDN, application, SSL. And now there are multiple services, right, which are talking to different parts of our application. So should they be regularly checking with this agent before making the request to the actual services?
No, I don't think so.
No.
Like your actual request is a online system which the user will hit. This is for your monitoring purpose, that if something you see is not healthy, what appropriate actions you need to take. So for example, in this case, let's say the agent is monitoring health of one like multiple machines, and let's say if one machine is not healthy, your requests will be redirected to other machine. But this is just to alert the developers and all that this machine is not healthy, so what you need to do to make this machine healthy again.
Yeah, that's correct.
Tool. Yeah.
So end user doesn't need to bother about any of this thing. It is for continuous monitoring.
Mm-hmm.
But I think since it is exposed, it's up to the end user also, right?
Yes, but I mean, suppose we are developing a Facebook API, right?
Mm-hmm.
A Facebook application. We want to call Facebook API. Mm-hmm. We don't basically first say that whether the ping worked or not, right?
Yeah. Yeah, that's true.
Yeah, we normally go about it. A lot of time, those ping and all, those, what I have seen is that, from outside it doesn't work unless you have written ping controller. Normal ping and other stuff are blocked, maybe they allow only internally, not from the gateway. Yeah.
That's true. But I mean, the agent that is written for monitoring it, but that should also be checking if an external client is able to access those endpoints also, right?
Yeah,
Not
yeah.
internal
Understand.
one. Yeah.
Understand. So I understand. I'm saying that it's not probably public knowledge of that service.
Yeah, it's not necessary.
Yeah.
But it could, depending on how critical it is and like how critical it is for you to check the health before making the calls, depending on what kind of application you're using.
So, yeah, most of the time I have seen that if I write application, I don't bother if the service is running or not. I basically, try to see what error code I'm getting. And based on that, I take the decision. It's not that, first check the service, then make the call, and then still we have to handle the error code anyway.
Yeah, that's true. We usually depend on the SLA, right? If the SLA says, that's the reason they define this SLA.
Yeah.
Right? Yeah. We don't have to monitor it again. Yep, that's true.
So in Kafka, the clients do the handle the load balance, and I think the client handle the load balancing, right? So is that this agent gonna somehow expose to the client of Kafka, so that they can know what node is down, which one is up? They can route the request to that node.
I think Kafka, I think it works in a different way, right? Like it acts like a single system. It will have its own kind of monitoring. That's what I think. On an outside, if we are using Kafka as a one component of our application, then we need to have some mechanism to monitor Kafka, right? So
yeah, I don't think the internal nodes are exposed to anyone, right? You directly talk to the broker, and broker
yeah, that's what like
care of.
so for us, yeah.
Yeah.
So to ensure like Kafka will ensure its own cluster availability nodes, but for us, like whether the Kafka is available or whether we are able to place a message or consume a message, I think, yeah, that's what matters.
Guys, sorry. So in Kafka, what happens is the client itself can request all the brokers in the cluster itself, and the client takes care of routing the request to different nodes. So the question about whether to check for the health checks or not is actually depends on the context. So if you have the client has multiple endpoints to connect to, and it doesn't know, so the Facebook API thing that you're talking about, it's actually one endpoint that you're connecting to. So it's basically reactive handling of the status codes that you do. In the case when you have multiple endpoints that you can connect to, you can have a separate thread running that checks that individually checks each endpoint, and then you only always connect to the ones that are online. So this agent, this health checks, actually depends on the context that you are operating in.
Yeah, good point.
Yeah.
So one question, is it used in context? I mean, is it used, this pattern is used together with retry pattern by any chance? I was asked this question once in an interview, so just wondering.
So should agent also consider retries and consider success only after retries fail?
Yeah, I mean, like that is something that we can decide like when we are designing this health endpoint, right? Like if it responds one, it's most likely like whether it is up, and it's most likely up, right? Like, and this health check endpoints typically check very often. They don't like wait for hours to say again do another health check. So they try to do like if it's very high level system, maybe within second, every second it might check, or like every 10 seconds. because yeah, it depends on what's your availability requirements. Depending on that, like you will have the frequency of this health check endpoint. So it is effectively continuous pulling, right? Not retries is normally when something fails, then only you keep retrying.
So,
It's you don't retry, right? Like I don't know, like how that retry needs can be bundled with this.
so suppose Naga, this agent is what we are using to monitor the application, right?
Mm-hmm.
And then this agent, I'm assuming, would also raise alerts to people to look into it, right?
Mm-hmm. Yes,
This
correct.
agent is calling this endpoints like probably every minute, or
Mm-hmm.
I don't know if you want to do it every minute, every second,
Mm-hmm.
or maybe let's assume it is doing every 5 minutes check.
Mm-hmm.
And it called that endpoint and it failed.
Mm-hmm.
Should we include the retry pattern here and then raise the alert, or should we raise an alert
Yeah, so
immediately?
I can answer this.
Oh, okay, got it.
So
Yeah, go ahead.
basically, you are monitoring your application and you're collecting the metrics. Now, how you create alert? So you have to define a threshold. So you won't create alerts if you get 1 or 2 failures. You have some expectation from the service, this application, that out of 10 requests, probably 1 or 2 requests that is
We are
expected from
losing
the
your
application.
voice.
So then you will create alerts only when you see the failures above a particular threshold. And so that's why these monitoring services have these smart logic also, and algorithms and all machine learning algorithms, that they will see the pattern, that how many responses have been successful, how many responses have failed in the past. And if they see a deviation from the history, that usually 99% of the requests were successful of this agent, but today somehow 70% are only successful, 20% are failing, then it will create an alert. Or you can define your hard threshold. So those are the things that you have to do to create alerts.
Yeah. That's an interesting point of looking at the history based on previous day and today. But I think there are also like real-time systems where like you want to make sure this succeeds, right? Like you don't have time to like analyze the history. If this API fails, then we want, let's assume Facebook endpoint, right? If it fails, like we want to raise an alert, right? It
No,
cannot fail. I mean, like whatever it is that
some
Facebook.
requests might fail. So that's what I'm saying. If Facebook, if let's say 1 million customers are calling Facebook endpoint, if you are looking at the user endpoint, few requests might fail, and then Facebook won't create an alert, because it is expected that some requests might fail. Like there could be network issues, or there are so many bunch of issues that could happen. Only when, so that's why you don't see these services, they have 100% SLAs, right? Everything has like 5969 SLAs. So that means that it's not, you can ensure 100% availability of your service. Sometimes it will fail. You have to decide what is the
Okay. Yeah. So
so,
alerting
and
has to
what is
be
unexpected.
on the SLAs, you mean to say. Whatever
Yeah.
is
So,
okay.
yeah,
Yeah.
let's put in perspective, right? So suppose you have a load balancer. Probably load balancer, when it get first HTTP fail from a node, probably it will not call that node or send any signal to that node for, let's say, next 5 minutes or next 2 minutes, whatever you have defined, right? And then it will try to do again. If it gets success, then it will try routing traffic to that node. That is at load balancer level. But now you have this monitor to check the health and raise a live site issue to the developer or the whoever is the site maintaining the site, right? Typically, you do is that, okay, in last 30 minutes or last 20 minutes or last 10 minutes, whatever you can afford, if my 2 out of 5 call fail or 2 out of 10 call fails, right? So you are making every minute call, and in last 10 minutes, if 2 call fail or 3 call fails, then I will raise the alert. And this is a rolling 10 minutes. It will then keep doing that monitoring system. So I think the screenshot probably defines same thing, right? See, it is telling very true thing, individual and cluster, right? So some failure can happen. It bound to happen. A lot of time, your server get restart and everything is fine. Nobody need to bother about that.
That's right. I think like it all bounds to what is the SLA that you have mentioned on your application. That's where you define like whether 2 failures in last 10 minutes are okay, or is that how it is, or does it
Yeah,
directly
and
relate
like
to the
one
SLA?
important thing is that you should not create alerts on when your SLAs are breached, because if your SLAs are breached, then it's already too late. So
Yeah.
you have to create an alerts on a like higher. So like if you are giving customer 95% promise, then you have to create internal alerts on 97%, because if you have reached 95%, you have already broken the SLA.
Oh, yes, that's true. It cannot be
So
an
that internal term is called SLO, service level objective, that it's my objective, what I want to be 97. And the user agreement SLA is 95%.
Yep, perfect. Yeah, makes sense. Thank you.
Yeah, thanks. I think that was useful.
Yeah, that was just
So the answer is not using retry pattern in this scenario, right?
Yeah, I think we use, right, like that's what like I think I understood. So you basically depending on the threshold you retry, I mean like the same one, or you can also do, instead of retry, like send 10 different requests and see how
So
many.
retry won't be an individual request. Basically, most of the time it is saying that in last 10 minutes, how many calls are failed, because I'm calling every minute, something like that.
Mm-hmm. Okay. I think we covered most of this resiliency patterns. So I wanted to see if I mean, like I thought of initially going to this diodes and the throttling pattern, but like looks like we are just have like another 15 minutes, 20 minutes, sorry. Should we go them quickly, or like maybe we can just leave it for another pattern session?
I think we can take it to the next session.
I didn't get.
No, I was saying we can take in the next section.
Okay, got it. Okay, I think let's end this session and maybe we can discuss the plan for upcoming weeks now. And Bhavish, like, do you want to stop the recording? Maybe we can